I'm going to go a little out of order today, and that is because of the lab coming up. I'm going to actually skip to page 21 in the notes, and I'm going to talk about material that should be familiar, and that is material on the mole. But nonetheless, I'm going to assume there's a possibility it could be rusty for some of you, and I'm going to go over that. And this is because those of you who are in the morning labs, we need to use moles in our calculations on Thursday when we talk about experiment 4. So all we have to be able to do is go back and forth between moles and grams. Okay, that shouldn't seem too unfamiliar, but I want to at least make sure that I've reviewed it before I go over that with you in class. So, any questions before I get started about moles? You sure? Again, please do keep coming and seeing me in office hour. That's very helpful. I've had about 3 or 4 people today. That's unusual. I haven't had so many people before, and it definitely makes things better for me if I have questions to answer rather than just sitting there for an hour and a half. All right, so the mole is our big quantity unit that we use a lot in the sciences, chemistry and physics, for example. It's similar in type to units like dozens or gross. If you have a dozen of something, then that means by definition you have 12 of it. Good. So a dozen is a grouping unit, right? It's grouping things into a more convenient bundle. And if we are talking about eggs, obviously dozen seems to make sense. Now, we don't use dozens for atoms because compared to eggs, atoms are extremely, extremely small, right? If I had a teaspoon of, let's say, mercury, I mean, there would be trillions upon trillions of atoms in that teaspoon. It's a huge, huge number. So it makes much more sense for us that if we're going to want to deal with grouping units, we want to be able to group atoms into a very large set, not into 12s, but into something larger. And so we come up with a unit called the mole, and it is defined as this. We say that a mole of whatever it is we're talking about has 6.022 times 10 to the 23rd of whatever that substance is. And of course, this varies on what we're talking about. For example, if I'm talking about a mole of helium, this is rather important, and I think I have this coming up in a minute. But I say I have a mole of helium. Helium is an element, so what is the smallest piece of helium you could have? It would be an atom, right? The smallest piece of helium you could have is an atom of helium. Compared to, say, if I have a mole of water, what's the smallest piece of water you could have? H2O is a molecule. Good. So if I say I have a mole of helium, that means I have 6.022 times 10 to the 23rd helium atoms. If I say I have a mole of water, I have 6.022 times 10 to the 23rd water molecules. If I have an ionic compound, we're going to just say formula units as the phrase. Now, the definition of that, why that number, it was ultimately simply decided to be that the number of atoms that are found in exactly 12 grams of carbon-12. Yes, stop there. That's how it's defined. You could argue with whoever defined it, but they're probably long, long, long dead, so that wouldn't help. So that's how we've just decided it's going to work. All right, so as I just said a second ago, for a substance that contains individual atoms, helium or sodium, the word that we're talking about in terms of units is atoms. Talking about molecular compounds like water and carbon dioxide, it's a number of molecules. As I said a second ago, for ionic compounds, if I say I have a mole of sodium chloride, then I can't say I have a mole of sodium, I can't say I have 6.022 times 10 to the 23rd NaCl molecules because sodium chloride doesn't make molecules. Remember, we said it makes what kind of a structure?
Lattice.
A lattice, good. A crystal lattice is what we said. But it simply means that we can say that in that crystal lattice, there is a mole of sodium ions and a mole of chloride ions. Does that make sense? On the other hand, if I have magnesium chloride, because of that 2 being there, 1 mole of magnesium chloride means that there's 1 mole of magnesium ions and 2 times that for chlorines. So 2 moles of chlorides. That makes sense to everybody? Good. Okay, so let's just do some basic practice problems with this. So first question is, how many atoms are there in 4.55 moles of helium? So I'm just going to use a train track for solving this. If you are not solid with train tracks, I do have a handout under the handouts page on train tracks. This is just another way of writing a bunch of fractions being multiplied together. So what you're given is 4.55 moles of helium. And we abbreviate moles MOL. I don't know why we need to abbreviate a four-letter word, but we do. And to get to atoms, we're just going to use the definition of the mole. So I need to cancel moles by saying every 1 mole of helium contains 6.022 times 10 to the 23rd helium atoms. So, not too hard. And by the way, this is not an exact number. 6.022 times 10 to the 23rd is not an exact number. So it has 4 significant digits. The 4.55 has 3. So we're going to get 3 significant digits. I'm getting 2.74 times 10 to the 24. Excellent. All right, any questions on that? No. Example 2, I'm going to break into 2 parts. So I'm going to have part A. How many molecules are there in 0.125 moles of water? And part B. How many hydrogen atoms are there? Well, part A is no different than the last question. We're just given the number of moles and asked to go to the number of units. So in the case of water, it would be going from moles of water to molecules of water, right? But in part B, we want to get to hydrogen atoms. So let's just set some things up real quick. We know that for every 1 mole of water, how many hydrogen atoms are there in there? Each H2O has 2 hydrogen atoms. So if you have 1 mole of H2O, then that means you would have 2 moles, no, twice as much, right? 2 moles of hydrogen atoms. And if you were asked, how many oxygens would you have? 1 mole of oxygen. Good. Or you could have said 1 H2O molecule. Don't abbreviate molecule, MOL, okay? As what can we say? How many hydrogen atoms? two H atoms. And one oxygen atom. Or I could say three atoms total, right? Here's the Lewis structure. So hopefully you're familiar with that. The lone pairs. Okay. So this thing right here, HOH, that Lewis structure has, that's one molecule as a representation, but there's three atoms in it, right? Two hydrogens and one oxygen. Good. So I don't need that for part A, but I will need it for part B. So for part A, I'm saying how many molecules are there in 0.125 moles of water. So to go to number of moles of water, all we have to do is say, just like we did in the previous problem, 1 mole of the thing we're talking about, H2O, contains Avogadro's number of whatever we're describing. And in this case, the thing we're describing is H2O molecules. All right, so 0.125 times the Avogadro number is 7.53 times 10 to the 22. H2O molecules. That's not a problem, right? And significant digits here, we would have 3, good. And part B asked us to do this same thing for hydrogen atoms. Now I could start all over again, but that doesn't really make sense. So I'm just going to use this answer. And what am I going to say here? Every one molecule has 2 atoms. So I'm just going to take this number and multiply it by 2. But you should always show your work so we can understand exactly what you're doing. So if I've got 7.53 times 10 to the 22 H2O molecules, as we see here, every one H2O molecule has 2 hydrogen atoms. Good. So just taking the last answer times 2 gives me 1.51 times 10 to the 23. All right, do you have any questions about that? And if you were given the number of H atoms and you wanted to go to moles, you just go through this process exactly backwards, right? H atoms, there are 2 H atoms in a molecule, and then there are 6.0222. Every mole contains that many molecules. Okay, any questions so far? No. This, as we have already seen, I've skipped that. But it's something you should have seen in Chem 120. Ultimately, the numbers that appear on the periodic table in black, they all pretty much have decimals on them, except for the ones that have parentheses around them. Those are the synthetic elements. Those are the atomic weights. And those numbers, if I had started at the beginning of the chapter, they would have told you the mass of one atom of that element in atomic mass units. That only works perfectly for a few elements, like aluminum. For something like, for example, carbon, this number 12.01, that is the mass of the average mass of carbon atoms. Why do I have to say the average? Because carbon, yeah, it has 9 isotopes. Good. Remember, there's a mixture of 3 isotopes in nature. And so 12.01 is a weighted average. You did that calculation in 120, but we'll do it again probably on Thursday. So you'll see where these numbers come from. For aluminum, that's not the case because aluminum only comes in 1 isotope. Aluminum 27. Yes. Okay. So the mass of an aluminum atom is 26.98. And the units for that is what we call atomic mass units. I think in the textbook we use 120, we write AMU. In this textbook, they use the letter U. Okay. So as it says right there on the screen, the mass of a single aluminum atom is 26.98 U. Now, the whole way that the mole was defined and this whole scheme was defined, or the atomic mass units was defined, was to make this as convenient as possible. So what we're going to say is, yes, it's true that one aluminum atom has a mass of 26.98 atomic mass units, but 1 mole of aluminum has a mass of 26.98 grams. Exactly. And atomic mass unit is essentially just 1 divided by Avogadro's number, if we wanted it to convert it to grams. Okay. And so that's how that was designed. So which do you think we're usually going to want to know? The mass of 1 atom or the mass of 1 mole?
1 mole.
1 mole. Yeah. Are we ever going to be weighing out atoms? No. We're going to be weighing out things in grams. And so that makes more sense to use that number. So we call those atomic weights. And I'll use that term regardless if we're talking about atoms or moles. It should be clear from the units we give, whether we're dealing with grams per mole or U for individual atoms. So that works for atoms. What if the atoms join together to form molecules or they join together to form ionic compounds? We use the same numbers, but we just have to use the formula to add them. So a simple example here would be carbon dioxide. So let's find what's called the molar mass of carbon dioxide. This is sometimes called the molecular weight. Okay. So to do this, what I would see with carbon dioxide is I see that there's 1 carbon atom for every 2 oxygen atoms. So I could say there's 1 mole of carbon for every 2 moles of oxygen. And so this 12.01 is what? That is it. That's 1 mole of carbon that we see from the periodic table, right? And then the 2 times 16 is 2 moles of oxygen. Good. So we just take the mass of the carbon plus 2 times the mass of oxygen, and that's the mass of 1 mole of carbon dioxide. Very good. So you all remember doing that, I'm assuming, right? Yeah. You probably do that calculation more than any other calculation in chemistry, coming up with molar masses. Okay, then. So let's use this. So we now know how to go from number of moles to numbers of atoms or number of molecules. And we now know how to go from moles of something to grams and vice versa. So
let's look at this question. What is the mass in grams? And we are on page what right now? 22. What is the mass in grams of 2.50 moles of aluminum nitrate? Before we go anywhere, what do we need? Before we can do anything, what do we need to do first?
Name it.
Yeah, so we have the name, so we have to get the formula, right? So I'm going to show my work here. Aluminum, what is the formula of the aluminum ion? Aluminum 3 plus, right? And what's the formula of the nitrate ion?
3 minus 2 minus.
No, 3, 1 minus, very good. So the formula of aluminum nitrate, this has to add up to a 0 total charge, right? So every 1 aluminum needs 3 nitrates, good. And how are we going to show 3 nitrates? It's not NO33, right? It's going to be Al, and then we're going to use parentheses. NO3, 3, good. And I'll talk more about parentheses in about 20 minutes or so, very soon. We now need the molar mass of aluminum nitrate. For ionic compounds, we sometimes call this the formula weight. I just like molar mass better. So you don't normally need to write this out, but let's just go ahead and write it out. So the aluminum, there's only one of them, right? So it's going to be 1 times 26.98 grams, good. Plus, how many nitrogens?
3.
Yeah, we multiply by anything outside the parentheses. So there's 1 nitrogen inside, and we multiply by 3 from the parentheses on the out. So this would be 30 times 14.01, very good. Plus, and then oxygen, there's 9, right? 3 inside the parenthesis times 3 outside. So this would be 9 times 16.00. As I said a second ago, you're not usually expected to write this all out. You can just do this in the calculator. So long as you do it right, 26.98 plus 3 times 14.01 is what, 42.03? Plus 9 times 16. I'm getting 213.01. Is that what you're getting? Yeah, okay. I should have really written grams per mole. So 1 mole of aluminum nitrate has a mass of 13.01 grams. So to find the mass of 2.50 moles, very easy. We just, we're going to say, all right, you're given 2.50. Moles of aluminum nitrate. We need to cancel moles of aluminum nitrate. So this is saying 1 mole of aluminum nitrate has a mass of 13.01 grams. 1 mole. And I'm coming up with 533 in the calculator. Grams. Thank you. Any questions there? Now, for the lab on Thursday, or the pre-lab, when we start doing the advanced study assignment in the pre-lab, really that's the most that you need to be able to do, is be able to go from grams to moles and moles to grams. If you can do that, then you're fine. Let's do a little bit more challenging problem. How many oxygen atoms are there in 2.55 milligrams of aluminum nitrate? So we want to get from milligrams of this aluminum nitrate to actual oxygen atoms. Let's make a plan for this. What are you given of aluminum nitrate? And because there's two different substances in this problem, let's always be very clear which one we're talking about. We're starting with milligrams of aluminum nitrate. So this is how I make a plan. I'm going to use arrows to show what I'm going to go to next. And I ultimately want to end up with oxygen atoms. What am I going to want to do if I'm starting with milligrams? Yeah, I'll probably want to go to grams. Because in order to use the mole, which I know I'm going to need to use, based on recent experience, grams will be more convenient. Alternatively, you could use millimoles, but have any of you talked about millimoles in classes yet? Yeah. We'll wait until chapter 4 to talk about millimoles, but they're much more useful when you're talking about milligrams and milliliters of a solution. Once I know the grams of aluminum nitrate, I have a lot of power. I can use that to get to moles. Yeah, and then I can start talking about individual atom ratios. And once I have moles of aluminum nitrate, I can get to, there's a couple of things I could do here. Yeah, I'm going to probably use the ratio. So if I have a mole of aluminum nitrate, then what can I get to? Remember, we're going to oxygen atoms. Yeah, I can go to moles of oxygen. Good. Because the formula is telling me what? For every 1 aluminum nitrate mole, there are 9 moles of oxygen, right? 3 times 3. And once I know the moles of anything, it's easy to get to the atoms. So each of these arrows that I have written in my plan here is a step. I'm writing this plan because, again, it might not be obvious to you how to do this because it's got more than 1 or 2 steps. So if you're ever running into a problem on, a question, that's where you should start, is start with a plan. If it's self-evident how you're going to do this and you don't need a plan, then you don't really need to write one out. But I just assumed it might not be obvious. Okay, so we're starting with milligrams of aluminum nitrate, 2.55. But I mean, as far as I'm concerned, most of the time, that's probably a half to 2/3 of the points right there. Well, maybe not that much, but if you've got the plan right, the rest is just filling in the numbers and then hitting them in the calculator correctly. Okay, so we need to go from milligrams to grams. A couple ways you could do that. What's probably the easiest way? How many milligrams in a gram?
10 to
10 to the 3 or 1,000, right? So this isn't necessarily the way I always teach it, but 1,000 milligrams of something is 1 gram of it. There's many ways you could do that conversion. The way I taught it in Chem 120 was I would have said 1 milligram is 10 to the minus 3 grams. And is that exactly the same thing? Yeah. 10 to the minus 3 is 1 over 1,000. So that would work also. Oh, and I don't know why I put a 2 there. Ah, that was bad. Go away, evil 2. Should be a 3. Anyway. Just seeing if you guys are awake. All right. We're going from grams to moles now. So what are we going to do? We're going to use we calculated the molar mass. So 213.01. So down in the denominator, I'm needing to cancel grams. So the 213 goes in the denominator. Notice how I always go. I always go from, like in the case of magnesium, I went down a diagonal to the magnesiums, and then I go up. Then I go down and then up. So I'm going to go down on the diagonal here. So this was what, 213.01? Is 1 mole. And then here's the part that people mess up the most is the ratio. So if we've got aluminum nitrate, what are we going to say? Every 1 mole of aluminum nitrate has 9 moles of aluminum. Okay. In fact, you could have skipped that step and just wrote 9 moles of oxygen up there. Did I say aluminum? Sorry. But I think it's easier to just write it out this way. So 1 mole of aluminum nitrate has 9 moles of oxygen. And oxygen comes in what units? Oxygen is an element, so it comes as ions in this context. So every 1 mole of oxygen would be how many oxygen atoms? Yeah, good, the Avogadro number. So 6.022 times 10 to the 23rd atoms. For some reason, it's no longer called, again, the Avogadro's number is called the Avogadro number. Okay. It doesn't belong to him. It's the Avogadro number. So will I care? In reality, no. If you call it Avogadro's or the Avogadro number, but that's officially how it's supposed to be done these days. There's a group of chemists and physicists called IUPAC, International Union of Pure and Applied Chemists. They're the ones who come up with all the naming rules and the unit rules and everything. And they get together every now and then and create a fuss about these kinds of things. So anyway. So easiest way to put this in the calculator would be, here we go, 2.55. Multiply everything in the numerator, divide everything in the denominator. So 2.55 divided by 1,000 divided by 213.01 multiplied by 9 multiplied by the Avogadro number. And should we get a small or large answer, relatively speaking? If we're talking about atoms, it should be a very, very large number. And I'm getting 6.49 times 10 to the 19. Definitely practice putting all these things in the calculator because, you know, you don't want to be making silly calculator errors in the on the exams or any assignments. Could you try the next one yourself? It's going from nitrogen atoms to mass of aluminum nitrate. What if I say what mass? I'm not specifying units. What mass would normally make the most sense?
Right.
Grams, yeah. So let's do that in grams, even though the last question was in milligrams. If you want to start with a plan, you can start with a plan. But I think if you look at this question, you're given numbers of nitrogen atoms and you want mass. So compared to the last question, it's almost the same question, except you're working backwards, and instead of oxygen, you're doing nitrogen. Good. So would you try that on your own then? You all have the question written down in your notes, right? Okay. I'm going to turn off the screen. They'll have it ready. Okay. So that way I can do the question. And I'm going to turn off my screen on the video. Same thing. And I'm going to pause recording. Okay. So yes, I will talk about that shortly. All right, so we're going to convert nitrogen atoms, first of all, to moles of nitrogen, right? Dealing with individual atoms is inconvenient. So we're just going to use the Avogadro number. And by the way, there are a couple ways you could do this in terms of order. But to me, it makes the most sense to go from nitrogen atoms to moles of nitrogen. And then we're going to go from moles of nitrogen to aluminum nitrate. So in the problem above, 1 mole of aluminum nitrate was 9 moles of oxygen. What about nitrogen? Instead of 9 moles, it's 3. Excellent, good. So there are 3 moles of nitrogen for every 1 mole of aluminum nitrate. And then finally, we would like to get to the mass. And for that, we have the same molar mass, 213.01 grams of aluminum nitrate for every 1 mole. Good. And then doing this gave me the correct answer. Now, when I did this in the calculator, I typed in 19.45 divided by 6.022. Why did I do that instead of like this as written? To save me some time, 10 to the 24 over 10 to the 23 is just 10, right? Yeah, 10 to the 1, which is 10. So I just multiplied this by 10, 19.45 divided by 6.022. And then I just saved myself a few steps, okay? If you have to take the time to stop and talk about it like I did, that would waste time, okay? But if, just fewer steps, it's better for getting through things fast. And this problem, unlike most of the others, had 4 significant digits, correct? Good. Is 1 mole of aluminum nitrate 3 moles of nitrogen? Why did I not say 1 significant digit there? It's an exact number. Exactly. The numbers of atoms in formulas are always exact numbers because they're countable. You can't ever have fractions of atoms. This is one of the things that makes me cry on exams. When I ask how many atoms there are and someone says there's 1.25 times 10 to the minus 22 atoms. Why would that be totally wrong? Other than 0, what's the smallest number of atoms you could ever have? 1, right? What is this number? It's not negative. It's way less than 1. What is this number? It's 0.00000000125, which is way less than 1, right? If it was negative, it'd have to be a negative here, right? And can you have negative atoms? No. The smallest numbers of atoms you can have is either 0 atoms or 1 atom, right? Nothing in between. Just like, do we ever talk about I have 1/7 of a human being? I mean, that'd be really gross. That doesn't make sense. So human beings don't come in fractions and neither do atoms. Okay. Go away. Why aren't you going away? All right, well, The box has decided it's going to hang out and not leave. There it goes. All right, so you have the answers. I'll pick up with percent composition on Thursday because I don't need percent composition right now. And I'm going to go back to chapter 2 where we left off. I just want to make a quick note. I'm going to write these down, even though these have nothing to do with the topic, but just a quick reminder, because we talked about nitrogen a minute ago, and we said that it's actually found as pairs. Can you remind me, please, what are the diatomic elements? Let's do them in order of lowest mass to highest mass. So the first element on the periodic table that is diatomic is hydrogen. Very good. And then nitrogen. After nitrogen is oxygen. And then the rest are all, what do they all have in common?
Group 7A.
They're group 7A. They're all halogens, right? So F2, Cl2, Br2, I2. A question comes up in the lab, lab 12, so a long ways away. What would astatine probably be if you were to guess? AT or AT2? Yeah, I think it's a reasonable guess. I don't know if we have experimental evidence. I'm sure somewhere someone has answered that question. But remember, I said astatine is so incredibly rare. We're not likely to find it. It would have to synthesize it through a nuclear reaction, but it would probably be AT2, right? Let me ask you this. This is experiment 12, so I'm cheating a little. Fluorine and chlorine are solids, gases, or liquids at room temperature? Fluorine and chlorine? They are, you guys don't know about chlorine? Gases. Yeah, actually, there's a horrible train derailment going on right now in Ohio, which involves, I think, one of the tankers is full of chlorine gas. Okay. It's crazy. This tanker is full of, one of them is full of phosgene and another is full of hydrogen chloride. Phosgene, which I had to work with in grad school, you get one breath of phosgene and 8 hours later you die of pulmonary edema. You basically drown. Your lungs all liquefy on you and you drown internally. Not a nice way to go, okay? I'm like, they're transporting this? But anyway, and they say it was going to blow up, so they had to vent it into the air. Okay. And people were like, I'm not going to leave. I'm not going to. Yes, you're going to leave. Okay. You're not going to inhale phosgene. And then what does HCl turn into as a gas as soon as it hits water? What do we call HCl most of the time? Hydrochloric acid. So as soon as it hits water, oh, that's terrible. You breathe that, your lungs turn into hydrochloric acid. So chlorine, just about as bad. So anyway, yeah. Fluorine and chlorine are gases. Bromine is a liquid. Iodine is a solid. So what is astatine? Probably. Following the trend. A solid, wouldn't it be? Right? Gases at the top, then liquid, then solids. Yeah, because it's heavy. Okay. We don't really know. But if we had enough, that's probably what it would be. There are other elements that you do not need to know, and I'd rather you not at this point, but phosphorus, sometimes we write as P4. What does that mean? It's found in groups of 4, okay? This is a problem because there's many different allotropes of phosphorus. Allotropes meaning way it's found. Carbon, for example. What are the 2 ways that you commonly find carbon in nature? One much less common than the other. Diamond. So pure carbon can be diamonds, or it can be found as graphite. Okay. There's other forms too. So phosphorus can be found in 4 ways. they're all colored names. So white phosphorus, black phosphorus, red phosphorus, and violet phosphorus, and they would all have their own formula. Sulfur is almost always found as what we call sulfur flour, which is a yellow powder, and it is 8. No reason to memorize that, okay? But they don't get featured as much, so in case they get lonely, there are other numbers besides 2 out on the periodic table. All right, going back to naming. So the only reason I bring that up is I think in some labs or some homework problems, you'll see them write phosphorus as P4, okay? And if they don't write it like that, you would just say when you balance the equation as P, it'll probably have to have a 4 in front of it. So it doesn't really matter. The diatomics, it's very important. All right, so going to the polyatomic ions, I had asked you to please make sure to learn all of these or review all of them before coming to class. I think that's Thursday, but definitely today. So a polyatomic ion is just an ion that has 2 or more atoms in it. They go from rather simple ones like hydroxide, which is OH, to some fairly complicated ones like acetate, C2H3O2, 1 minus, as far as these goes. There are not many polyatomic ions which are cations. They're almost all anions. And in the charts I gave you in the notes, you notice they all have negative charges. The only really important polyatomic ion that's positive is ammonium, NH4+. There is a slightly weird case that I sometimes do ask in this class, and that is the mercury 1 cation. It's Hg2 2+. So that's kind of like the diatomic elements we just talked about, except instead of being an element, it's an ion, okay? So unlike oxygen, oxygen comes together, you've got 2 atoms. With mercury, they would come together and then throw away 2 electrons at the same time. Tends to be rather unstable, means it likes to change from Hg2 to 2 plus to just plain Hg2 plus. Why is it called mercury 1 if there is a 2 plus on it? Yeah, the only way this formula could work is if each one of them has a 1 plus charge, if we think about it that way. Okay. And left to its own devices, 1 mercury will wander off with both electrons. So that means one of the mercuries just becomes plain mercury, Hg, and the other becomes Hg 2 plus. Okay. The vast majority of the ions are negative, and they are oxyanions. And when I say oxyanions, that means they contain oxygen. And for our purposes, all of the oxyanions also end in, that you had to know, end in ate, A-T-E. So on this table, the only ones that are not oxyanions are hydroxide, which does contain oxygen, right? But it's oxygen front. Cyanide, which has no oxygen in it. And peroxide, which does have oxygen, but it's special. I will very rarely talk about peroxide because it tends to make naming these things very difficult. And so if I want to talk about peroxides, I'll be very specific about it. Thiocyanate is, I guess you could say, an honorary oxy ion, even though it doesn't actually have any oxygen. All right, so we want to know those. So hydroxide and peroxide, not considered oxyanions. A reminder about parentheses. Students often use parentheses incorrectly when they're writing formulas. The 2 ways to write them incorrectly would be to add them when you don't need them or to not write them when you do need them, right? So let's be clear. For ionic compounds, there's only one circumstance where you ever use parentheses, and that is for a polyatomic ion when there are 2 or more of them in the formula, okay? So you never use them with monatomic ions, like sodium, aluminum, lead, any of those. So only polyatomic ions, and only when there has to be a number outside the parenthesis. You can't write a parenthesis with no number on the outside. That doesn't make sense. So these examples that I give here, magnesium nitrate and ammonium sulfate, make sense because magnesium has what charge? 2+, and nitrate has only a 1- charge, so you need 2 of them. And so that's why we put a parentheses around the nitrate. And ammonium sulfate, same idea. Ammonium is +1, but sulfate is -2, bless you. So we need 2 ammoniums to do what such important thing on ionic compounds to make the charge, to neutralize, to make the charge add up to 0. That's so important for these compounds. Good. So these are all incorrect here. NaNO3 with parentheses is incorrect because if you only need 1 nitrate, you would never put parentheses. Someone would understand it, but I would say, ugh, and my stomach would revolt looking at that. Okay. BaCl2 is incorrect because yes, you do need 2 chlorines, but it's not chloride's a monatomic ion. So you're trying to group something that doesn't need to be grouped. So don't use parentheses around monatomic ions. And then this example, MgClO32, should seem obviously wrong because there's no 32 on any of these things. What did they mean? They meant ClO3 in parentheses with a 2. Okay. You do agree the way that's written technically does say oxygen 32, right? Yeah, so we don't do that. So these again are in your notes, all the most common polyatomic ions. Unfortunately, this is nowhere near an exclusive list or an exhaustive list because there's the 8s, but who else is out there if you remember? The ites. T is in tine, E, or T is in Tom, E. So how are the ites related to the 8s? They have 1 less oxygen, yeah. So let's look at there's very few polyatomic ions that have a complete family. Chlorate has a complete family. So chlorate is ClO3-. But there's 3 relatives that differ only in the number of oxygens. There's perchlorate, chlorite, hypochlorite. Those all are definitely found in nature, in compounds that we use here. So first of all, what are the 2 things, bless you, that they do have in common? They all have chlorine and oxygen. And the other important thing that all 4 have in common is they're all -1, right? None of them are -2, -3, +1. So in a family here, they have the same elements and the same charge. The only thing that changes is the number of oxygens. So starting with chlorate, if you add an oxygen, what do you have to do to the name of the ion? Add per in front, yeah. So per means you've added an oxygen, okay? You've heard of permanganate, right? I don't think I've ever heard of manganate, but what would manganate be if permanganate, I don't have it on, there it is, sorry. If permanganate is MnO4-, if manganate does exist, what would it be? MnO3, because per means you've added 1 oxygen, right? So, good. As I said, I've never heard of manganate. Maybe it exists. Okay, so if you take the 8 form, the 8 form again is for the ones that you've all learned that end in 8. And if you add 1 oxygen, then you have to change the name to per in front of the ion. That makes sense to everybody? So persulfate, sulfate is SO4 2-, so persulfate would be SO5 2-. By the way, just because you can do this in name doesn't mean the ion really exists, okay? Persulfate does exist, but I mean, I wouldn't have even known that until maybe 9 or 10 years ago when I found out that it's good for a certain reaction I wanted to do. Okay. I don't think we have any persulfates anywhere in our stockroom. All right, so take your 8. If you take away an oxygen, the only change in the name is 8 becomes ite. So ClO2 minus is chlorite. And if you take away another oxygen for 2 total, not only do you change 8 to ite, you have to add hypo in front. Okay. Pair will never begin. If something begins in pair, it must end in 8. And if something begins in hypo, it must end in ite. Okay? Good. So there's no pair-ites or hypo-8s. They just don't exist. This is not to be confused with ID as in dog E. Ides. When do we have ides? Other than hydroxide and cyanide and peroxide, when do we have IDE? Yeah, when it's the element by itself, right? No oxygens. So Cl minus is chloride. Yeah. So even though it's not in the family, if I was to write it here, chloride is Cl minus. So ATE and ITE all have oxygen except for what's it called? Thiocyanate. What does thio mean? Can you figure out the pattern here? We've got thiocyanate here, and we've got in the 1 minuses, and we've got thiosulfate. Technically, what does it mean? Can you figure it out? What element does it have to do with? Thio is always referring to the element sulfur. Good. Thio means change 1 oxygen into sulfur. Okay. Does that make sense? Cyanate is OCN. Thiocyanate, you changed the 1 oxygen into a sulfur. Sulfate is SO4 2 minus. Thiosulfate is you take one of those 4 oxygens and change it into a sulfur. So instead of being SO4 2 minus, it's now S2O3 2 minus. Okay. It's not really worth memorizing that rule because those are the only 2 that are important. If in organic chemistry you learn about compounds called thiols, what is that going to mean? They contain sulfur. Yeah, thio. Now, the dumbest of all rules, if it begins in mercapto, it contains what element? Sulfur. Because mercaptos are things that react with mercury, which means sulfur. It's the dumbest thing I've ever heard in my name. Okay. I mean, in my life. Okay. But I think there's a thing they used to put on your ouchies when you got cut. They ban it now because they think it causes cancer. So sometime around the time I was a child, and it has like mercapto something or other in the name, and it's got mercury and thimerosal. That's it. Oh, I'd have to go look it up. All right, I'm on a tangent. Let me get back to normal here. All right, so anyway, we have that. Some other changes to the anion. If you stick an H in front of these ions and you increase the charge by 1, you have to add the word hydrogen in front of the name. Or in special cases, you add the prefix bi in front, not to be confused with di, which means 2. Good. So there's not very many of these. So CO3 2 minus is carbonate, right? If I add H plus in the front, I have to change the charge from 2 minus to 1 minus. And I now name this bicarbonate or hydrogen carbonate. To be safe, hydrogen always works. And that's always the safest way to name it, hydrogen carbonate. Okay, and it's very common. It's not rare. So we have to be familiar with that. You can name it any way you want, but if I say on an exam bicarbonate, and experiment 5 is all about bicarbonates and carbonates, you need to know that ion. Sodium bicarbonate is very famous. What is it used for at home? It's called baking soda. Yeah. Baking powder is, I want to say sodium carbonate, but I'd have to go look it up. Okay. So sodium bicarbonate, NaHCO3 is bicarbonate. That's what that is. What would this be called? What are the two acceptable names for that? Yes, sulfate we know is SO4. So if this is SO3, it's sulfite. Good. So it would be called either the bisulfite ion or hydrogen sulfide ion. Yeah. Will it ever be found by itself? No, it's always going to have a chaperone. An anion will always have a cation. So you can't buy bisulfite. You can buy sodium bisulfite, potassium bisulfite, copper 1 bisulfite. You get the idea, right? So they will always come with a partner. Good. Now, you can't add a second hydrogen because what would happen to the charge? It would go neutral. So you'll notice this carbonate is 2- and sulfite is 2-. You can't do this to any of the 1-. Like, for example, nitrate, if you add an H+ to the front, it's no longer an ion, it's neutral. What do we call those compounds where you add enough H's to the front to cancel out the charge? They're very common. We haven't talked about them yet, but they are acids. Acids, okay? So HNO3, does anyone know the name of that? It's not hydrogen nitrate, it is nitric acid. And HClO3 wouldn't be hydrogen chloride, it would be chloric acid, not hydrochloric, but chloric acid. Good. So you can add 1 hydrogen to the 2-. So you can get bicarbonate, you can get hydrogen oxalate. The only time you use bi, you don't need to memorize this. You only use bi for carbonate and sulfate and sulfite. No one else, I've never seen it used, for example, for the others. You can do that with the phosphate and the borate too, but you can only add 1 hydrogen. If you add 2 hydrogens, you no longer have that compound. It's an acid. So adding 2 hydrogens to the front would be carbonic acid. Adding 2 hydrogens to the front of sulfate gives sulfuric acid. Good. Phosphate, though, because it's 3-, borate also, you can add 1 hydrogen and it's hydrogen phosphate. You can add a second hydrogen and it's still going to be negative. So that would just be called dihydrogen phosphate or dihydrogen borate. And if you add 3 hydrogens, it's no longer an ion, it's now phosphoric acid. Good. All right. Now, so it's important when you look at a compound, like, for example, let's look at potassium dihydrogen phosphate. There's only 1 cation here. What is the cation? The cation is the potassium, right? So when I say you're sticking the H in front, the H belongs to the phosphate. So if I ask you, what's the cation is potassium. The anion is dihydrogen phosphate. Yeah, H2PO4. -1. Yeah, good. Okay. So those are tricky sometimes because people want to stick the H's and say the cation is potassium dihydrogen. No. If I drew this as a Lewis structure, we would see that the Lewis structure looks something like this. You don't have to draw it. If it's an ion to this point in time, what do you have to do if it's an ion? You need to put it in brackets. Okay. Good. Okay. So you see the hydrogens clearly belong to this ion, right? They don't belong to the potassium. And then what kind of bonds are these? So these are covalent bonds, right? The OH, all the straight lines are covalent bonds. What kind of bonds going to happen between the potassium ion and the dihydrogen phosphate ion? Ionic, good. And again, those are going to make crystals, right? So I don't know why this means crystals, but it does for me. Okay, here's a potassium, here's a biphosphate, here's a dihydrogen phosphate, here's a potassium. To make things really stupid and confusing, this is actually almost never called that. It's almost always called potassium phosphate monobasic, and I won't explain it, so don't worry about it. Okay. It's because some people decide that they have to make things much more complicated. So if you go and get that compound in they have a whole new name for it. All right, so we're going to wrap up with a couple examples, and then I'll talk about type 3 compounds, which is something that's pretty easy to do. And we'll leave acids for Thursday. So let's name each of these compounds, please. First of all, type 1 or type 2. Type 1 means that the ion only makes one charge. So lithium is always 1+, so it's a type 1. Magnesium is in group 2, so it's always +2, so it's a type 1. Lead is not in group 1, group 2, group 3, and it's not one of the 3 special ones. Who were the 3 special ones? Do you remember? Zinc and cadmium are +2, and silver. Silver is definitely a type 2. So this is a type 2. That means we have to put the parentheses in the Roman numeral in the name. That's all that means. So gold is not one of the special ones, so it is a type 2. Potassium is it's always +1, so it's a type 1. Start going a little fast here. What's the name here of this compound? So lithium sulfate. Very good. By the way, if you do watch the videos, I'm noticing I don't think, like, you can see my cursor here, right? After the word lithium. For some reason that doesn't seem to record on Zoom. So I know sometimes where you're watching it, I say this here and that here, you'll be like, what is he talking about? And the thing is, I'd have to have a mouse on top of all this, and that gets really confusing. So I'm sorry if you can't see where I'm pointing. Okay, the next one, it looks like magnesium sulfate, except what? Yeah, exactly. It would be magnesium sulfate if it was SO4, but we're missing an oxygen, so sulfate becomes sulfite. Very good. Magnesium sulfite. Okay, lead, on the other hand, we need to know its charge. Okay, IO3 is what is iodate, right? So IO4 is periodate. Good. And what's the charge of iodate and periodate? It's -1, and there's two of them, so it's 2 minus, so the lead would have to be 2 plus. By the way, I will almost never ask you to say, is this a type 1 or a type 2? It's just something you have to ask yourself before you name them. Gold is a type 2, which means I'm going to have gold, parentheses, and then chloride. And the charge would be the chlorides are 3 minus, so the gold would be 3 plus. And then this final one, potassium, there's a hydrogen there. So if that's carbonate, then the H in front makes it bicarbonate or hydrogen carbonate. Now, you don't need to give me two names, but as I think I'd said a second ago, I could give you either name. So you need to know what I'm talking about. So, any questions on these? Yes. Oh, bicarbonate. I'm sorry. Thank you. Yes, that's what my brain was saying. I think I said it in words, didn't I?